We've all seen what transformers can do. They write poetry, they generate code, they can translate languages with this spooky, almost human-like understanding of context. And their secret weapon? It's a mechanism called self-attention. But here's the paradox. This incredible power comes with a staggering, almost crippling computational cost. And unpacking that paradox is exactly what we're going to do.
So this is the central question, right? It's the one that keeps anyone who's tried to push these models to their limits up at night. The attention mechanism, it really is a double-edged sword. It's what unlocks all these amazing abilities, but at the same time, it creates this computational nightmare that for a long time has felt like a hard ceiling on what we can even do.
And here are the stakes, laid out plain and simple. On the one hand, you get this almost magical ability for the model to understand how words in a sentence relate to each other, no matter how far apart they are. That's the power. But on the other hand, there's the price. And if you've ever tried to train a large model, you have felt this price. That dreaded out-of-memory error on your GPU, the training runs that seem to take forever, the hard limit on how much text you can even feed the model at once, it all comes back to this one single core paradox.
Okay, so to really appreciate the genius solutions that are now shattering this barrier, we have to roll up our sleeves and get our hands dirty with the problem itself. Let's build up the intuition for where this n-squared nightmare actually comes from first principles.
It all starts with three concepts: query, key, and value. Q, K, and V. Here's a way to think about it. Imagine for every single word in a sentence, we create a query. It's like that word is standing up and shouting into a crowded room, "Hey, who in here is relevant to me?" Then every other word in that room holds up a key, which is kind of like a name tag describing what it's all about. The query scans all the keys to find a good match. And for every relevant key it finds, it asks for that word's value, its actual substance, its meaning. Finally, it gathers up all those values and blends them together to create a brand new understanding of itself, one that's now super rich with context from everyone else in the room.
Now, mathematically, this is what it looks like. But don't let the formula intimidate you. I want you to ignore everything else and just focus on one part, the very first operation inside those parentheses, Q times K transpose. That's it. This one, simple-looking matrix multiplication, this is the problem child. This is the source of all our pain. It is the computational bottleneck that creates the entire n-squared nightmare. Let's see exactly why. Let's visualize it. Imagine we have a sequence of n words we're feeding into the model. Our query matrix Q is going to have n rows, one for each word's question. And our key transpose matrix is going to have n columns, one for each word's name tag. So what we're about to do is multiply an n by d matrix with a d by n matrix.
And boom, this is the result. A massive, enormous n by n matrix. Every single word has now been compared with every other single word. Think about what that means. If you have a sequence of, say, 4,000 words, you've just created a 4,000 by 4,000 matrix. That's 16 million numbers you have to store somewhere. And here's the killer. If you double your sequence length to 8,000, you don't double the memory, you quadruple it. This is quadratic scaling, and this n by n matrix is the memory monster at the heart of it all.
So a totally natural question to ask right now is, okay, yeah, it's big, but our GPUs get faster every year, right? Can't we just throw more hardware at the problem? And that is such a seductive thought, but it actually misses a much more subtle and much more important bottleneck.
You see, the real problem isn't just about raw calculation speed, what we call flops. GPUs are ridiculously fast at doing math. The real issue is memory bandwidths, how fast you can move data around inside the chip. Think of it like this. Your compute speed is the speed limit on the highway, and that's getting faster and faster. But your memory bandwidth is how many lanes the highway has. And if you have a massive traffic jam, it doesn't matter if the speed limit is 100 miles per hour, nobody's going anywhere.
And that's exactly what's happening inside the GPU. This giant n by n attention matrix is way too big to fit in the chip's tiny, ultra-fast local memory, the SRAM. So, to do the calculation, the GPU has to write this whole monster matrix out to its much slower main memory, which is called HBM. And then, for the next step of the formula, it has to read it all the way back in again. It's this slow, painful round trip that creates a massive input/output, or I/O, traffic jam, and it just grinds the whole process to a halt.
So if the real problem is an I/O traffic jam, how in the world do you solve it? Well, the first approach is just a beautiful, beautiful piece of low-level engineering.
Instead of trying to brute force your way through the traffic or build a wider highway, what if you could just avoid the highway altogether?
This brings us to a groundbreaking paper called Flash Attention. And seriously, the title tells you everything you need to know. 2 keywords here. First, exact. It computes the exact same attention result. No loss in model quality, none. And second, it does this by being I/O aware, by fundamentally understanding and redesigning the whole process around that memory bottleneck we were just talking about.
Here is the core insight, and it is so clever. The creators of Flash Attention realized they never actually had to build that full, monstrous n-by-n matrix in that slow memory at all. Instead, they could break the problem into smaller, much more manageable pieces or tiles. They just load a small block of Qs and Ks into that super-fast on-chip SRAM, compute their little piece of the attention puzzle right there, combine it with the Vs, and then immediately move on to the next tile, only ever storing the final, small result. By staying completely within the fastest memory on the chip, they basically avoid the traffic jam entirely. It's genius.
Okay, so that's the engineering solution. Be smarter about how you use the hardware. But there is a completely different path you can take, an attack from a totally different angle. This one is pure mathematics. What if you could just change the formula itself so that the problem never gets created in the first place?
The crucial difference here is the order of operations. It's all about the parentheses. Standard attention forces you to multiply Q by K transpose times first, which is what creates that n-by-n beast. But look at the reordered version on the right. What if we could multiply K transpose by V first? Well, K transpose V creates a tiny matrix of size d by d, where d is just the embedding dimension. Think maybe 128 instead of 4000. This completely sidesteps the memory monster. Now the catch, you can't just reorder matrix multiplication and expect the same answer. To make this move mathematically legal, you have to find a clever way to approximate that pesky softmax function.
And the tool for this job is a classic from the mathematician's toolkit, called a Taylor expansion. Think of it like trying to trace a really complex, curvy line. You can approximate that curve using a bunch of simpler shapes, like straight lines or gentle parabolas. Early linear attention methods used a simple, first-order approximation. That's like using a straight line. It was fast, yeah, but it lost a lot of the nuance of the original curve. The key innovation in a model like QT-VIT is that they use a more powerful second-order or quadratic approximation. That's like using a parabola. This lets them do that reordering trick while capturing much more of the original softmax function's behavior, which leads to way better performance.
Okay, so we have 2 brilliant solutions on the table. One from hardcore engineering and one from elegant mathematics. But how do they actually perform when the rubber meets the road? Let's take a look at the results.
This chart just says it all for the I/O-aware approach. This is the speedup you get from Flash Attention compared to a normal implementation on a powerful A100 GPU. At a sequence length of just 1,000, it's already twice as fast. At 4,000, it's 4 times faster. You can see the speedup just gets more and more dramatic as the sequence gets longer, because that's exactly when that I/O problem really starts to choke the standard approach.
And what about memory? Well, the savings are, honestly, they're even more staggering. At a 4K sequence length, Flash Attention uses 20 times less memory. Let that sink in. This isn't just a little incremental improvement. This is the difference between your model training successfully or crashing your GPU. It fundamentally changes the entire scale of problems you can even think about tackling.
Now let's check in on the math-based solution. Here you can literally see what that more accurate approximation buys you. On the left, you've got an attention map from a simple first-order approximation. It's kind of fuzzy, a bit diffuse. But on the right, with QT-VIT's much better second-order approximation, the attention map is so much sharper, so much more focused. Look at that. When you ask about the dog's left ear, it correctly lights up on the right ear too. It's capturing much more meaningful relationships in the data.
And that focus, that sharpness, it translates directly into performance. Check out this comparison from the paper. QT-VIT achieves higher accuracy than the baseline model while using nearly a third of the computations. That is just incredible. It proves that a smarter mathematical approximation isn't just about being more efficient, it can actually lead to a better, more effective model overall. So after all of that, what are the key mental models you should walk away with? First, the next time you think about the attention bottleneck, remember, it's not a compute speed problem. It's a memory I/O problem. It's a traffic jam. And second, there are 2 primary, elegant escape routes from this n-squared nightmare. You can use smarter engineering to just avoid the traffic jam entirely, like Flash Attention does, or you can use smarter math to change the calculation itself so the traffic jam never forms, like the whole family of linear attention models are doing.
Look, these breakthroughs are fundamentally reshaping what's possible. They are the engines that are driving us toward models with context windows of 1 million tokens, maybe even more. And that leaves us with this really fascinating question to think about. As this quadratic barrier continues to crumble away, what entirely new applications and capabilities are going to be unlocked? What happens when a model can read and reason over an entire book or a whole code base in a single pass? The future of AI is being built on these kinds of clever ideas right now, and it's going to be absolutely amazing to watch.